Good morning and good afternoon and good evening. So welcome to Micro 2021. This is the tutorial on AHS, a Agile framework for hardware specialization and software mapping. So first of all, I would like to introduce the team. So my name is Yu Liang. I'm currently an associate professor at the School of ECS, Peking University. So the other four presenters are all my PhD students. They are Liqiang Lu, Liancheng Jia, Side Zheng, and Zizhang Lu. I also would like to acknowledge some of our collaborators who contribute to the technique I will introduce today. So I would like to thank Professor Jason Kong from UCLA for giving us a suggestion on the space-time modeling part. I would like to thank Jieming Ying and Xue Haiqian for the NOC modeling and hardware software co-design part. I also would like to acknowledge two of my students. Qingcheng Xiao is a recent PhD graduate student from my group, and currently he is a senior engineer at Huawei. He is the main author of Haskell work. Naiqing Guan is a recent undergrad student graduate from my group. Currently, he is pursuing his PhD degree at the University of Toronto. He is the main author of Tanit. This is the schedule of AHS. Basically, I will first give an overview of the AHS framework. Then we will move to the technical section. In this technical section, we will introduce four tools. They are Haskell, Tanit, TensorLib, and the Flex Tensor. So for each tool, first we will give a brief technical talk to introduce the technique behind it. Then we will give a hands-on lab exercise. So in a lab exercise, we will introduce the code and also give a detailed instruction on how to use the tool to solve problems. There will be 10 minutes in between. And for each talk, we will have a time for Q&A. So please use Zoom Q&A feature to do that. Also, Micro 2021 will record the video and the slides, and also the slide and video will be available on the AHS website. Okay, so this is the outline of my talk. First, I would like to give the background, so why we are doing this. And also, I would like to introduce the challenge we're facing. Finally, I will give the overview of AHS. Okay. So the ending of Moore's law coupled with the rapid growth of various applications, including artificial intelligence, communication, and graphic, and so on, had led to this domain-specific architecture. Domain-specific architecture, short for DSAs, has many advantages. I just want to list a few here. So from the hardware perspective, we can design a more efficient parallel architecture, memory hierarchy, bit width, and so on. From the software perspective, we can simplify the programming system by defining a domain-specific language and compiler. The particular domain we focus on in this tutorial is the tensor computation, which finds application in many domains, including computer vision, natural language processing, social network, and so on. So for these applications, they often organize the data in multi-dimensional arrays, which are known as tensors, and then perform computation on top of that. So here I list some typical use tensor computations. They are GEM, MTTKRP, 2D-COM, TTMC, and the stencil. So for these computation, they are very regular computations. So they can be represented using a perfect nested loops like this. But different tensor computation, they are still different in terms of the tensor size and also the way they reduce the data. Overall, tensor computation tends to be regular with high parallelism, but at the same time demands huge computation amount. And because of this huge computation amount, recently this spatial data flow accelerator have been shown to be an effective platform for accelerating these tensor computations. So in this spatial accelerator, it normally use two-dimensional PE arrays with customized interconnection and memory hierarchy. So for each PE, it can contain its own register and local memory. And all these PEs will share the scratch pad. And this spatial accelerator is very efficient because it offers high parallelism, high data reuse, and it is also energy efficient. However, to design the entire hardware software stack for this domain-specific architecture, there are several key challenges. The first is how do we partition the hardware and software? In other words, which part goes to the hardware and which part goes to the software? And currently, this is done manually. Second is how do we design the hardware rapidly? Currently, the common approach is to use hardware description language such as Verilog or HDL to do the implementation. However, this takes very long. And hardware only determines the peak performance. The actual performance actually is determined by the software. And also, we need the software to provide flexibility to handle different workloads. So the third challenge is how do we design the software efficiently? And the current approach is to write a low-level programming language such as assembly C or CUDA, which takes very long. So to summarize, so the entire software and hardware co-design process requires low-level programming, and it's very hard to optimize and takes long design period. And in the next, I will briefly talk about each challenge. Okay, the first challenge is about hardware software co-design. As I said, the tensor computation can be represented using loops. And given this loop nest, which consists of multiple loop iterations, and this hardware can only accelerate a subset of these loops. And the other loops will go to the software. And at the same time, this will set the hardware-software interface. But there are many ways to partition the loops between this hardware and software, and which one should we choose? And different partition has a different trade-off in terms of this efficiency, area, and so on. And the second challenge is hardware design. So for the loops to be implemented on the hardware, we have different ways to implement this. One of the most important parameters is this hardware data flow, which basically determines how this computation is parallelized and also how this data is moved between these PEs. For example, we can use multicast, we can use output stationary, row stationary, and reduction tree data flows. And to evaluate different data flow, we first need a data flow notation to represent this data flow. And then we need performance metrics to evaluate different data flows in terms of this data reuse, data access, latency, bandwidth, throughput, and so on. So after we figure out which data flow we need, we also, the next step is to implement them, but we have a different way to implement them. So we can have a Verilog-based, high-level synthesis-based, also a DSL-based approach. And this is a different approach. We have trade-off in performance, productivity, and flexibility. And the last challenge is the software design. So for the loops to be implemented by the software, we can use a sophisticated loop transformation to optimize this, including loop split, fusion, tiling, and so on. And this different transformation impact the final performance by influencing this locality and parallelism. And obviously, there is a huge optimization space, and with this non-trivial trade-off. So it's very difficult to optimize. So in the last few years, my group are mainly working on this AHS, is an Agile hardware and software co-design framework. So in this AHS, we leverage high-level abstraction, in particular this domain-specific language and the intermediate representation to address the challenge of low-level programming. And we use this machine learning algorithm to address the challenge of optimization difficulty. And we use this automatic synthesis tool and compiler to address the challenge of manual implementation. And now let me give you an overview of this AHS. So given this tensor algebra, our tool, Haskell, is a hardware-software co-design tool. Will partition the loop space between hardware and software and set the interface between them. Haskell use this tensor syntax tree as an intermediate representation to abstract the computation between hardware and software, and also use Bayesian optimization to do the design space exploration. And for the hardware part, our tool Tanit is a data flow modeling, notation and modeling tool. So it can return the performance metric for the given data flow, but the Tanit doesn't give the actual hardware implementation. So for the data flow, we are interested, then we can use another tool called TensorLib to generate a high performance chisel implementation. So the hardware part, we use this relation-centric notation as our intermediate representation. And also we develop complete synthesis tool. And for the software part, and our tool Flex Tensor can employ this sophisticated loop transformation to optimize the software part. And it uses a reinforcement learning based approach to do the design space exploration. And also it can generate the code for various backend with this intrinsic support. Okay, so all the resources related to this tutorial, including the slides, the video, the installation guide, and the code are available on the AHS website. And with that, I would like to welcome you again to this tutorial. And okay, I see there are some questions. Let me see. Are these slides available for download? Yes, I think the slides is already uploaded to the course website. No, to the AHS websites. So you can upload them. You can download them. Okay, let me see. There are some other questions. Can you explain the challenge one in more detail? Yes, so the challenge one is basically the hardware software co-design. So given this loop nest, we have multiple ways to partition the loop between the hardware and software. So so this is the challenge one. And so the first talk, actually, we will talk more details about this. If you still have questions, you can ask at the end of the talk. Okay, now we will move to the first one. It's a Haskell. Let me use the video.
Hello, I'm Zhang from University. In this section, I will introduce Haskell towards Agile hardware and software co-design for tensor computation. This is a work of my senior student, Xincheng Xiao, and a joint work for Professor Yu Liang at University of Southern California. With advances in algorithms, compute-intensive applications are applied to all aspects of our lives, such as computer vision, natural language processing, privacy, and security. The compute-intensive applications can be abstracted as computations between tensors, which are data organized in multi-dimensional arrays. Tensor computations feature a wide coverage, various scenarios, and a high demand for computing power. Tensor computations come in many forms, such as GEM in recommendation system, 2D convolutions in convolutional neural networks, TTM and MPDKRP in data compositions. There are various scenarios. From edge to clouds, there are censorships, edge compute devices, edge infrastructures, and cloud computers. From top to down, they require lower and lower power and latency. And from bottom to up, they require higher and higher throughput. In addition, A tensor application is often composed of many workloads. Take convolutional neural networks, for example. Their high accuracy is achieved at the cost of tens to hundreds of 2D convolution workloads. There is no sufficient computing powers on traditional CPUs. For instance, modern CPUs for smartphones need more than a second to accomplish a VGG-net-based object classification. This is often unacceptable. For tensor applications with various tensor computations and workloads, we can only design a dedicated accelerator shared by all the workloads. Dedicated chips based on FPGAs, CGRAs, and ASICs use different architectures from general-purpose chips. The dedicated chips can process tensor computations efficiently due to their massive parallelism and high energy efficiency. However, the chips provide efficiency but is fixed. We need software mappings to retain flexibility. The software mapping split a large tensor into subtensors and invoke the hardware execution for different workloads. We generate different optimized software mappings onto the chip. To this end, we define a combination of hardware acceleration and software mapping as a holistic solution for tensor applications. Generating the holistic solution at once is infeasible, as the hardware and software are tightly interweaved. For instance, loop reordering changes data locality, which impacts the efficiency of the memory hierarchy. The tile size decides the size of a sub-workload, which is restricted by the on-chip memory size. Therefore, it's a chicken or the egg problem that whether build chips without software evaluation or generate programs for a never-before-built hardware. To solve the chicken or the egg problem, a traditional design flow builds a dedicated chip first and then design adaptive software. This flow leads to a late system integration and poor solution quality, as the hardware cannot be modified after being typed out. In this work, we use a co-design flow to divide and conquer the problem. The co-design flow first partitions the design space, develops software and hardware in parallel, and integrates them together. Hardware-software co-design reduce the development cycles, allow deeply coupled optimization, and early feedback. There are several challenges in hardware-software co-design. First, we need to answer how to partition hardware and software. Then we need to explore design spaces efficiently. Also, we want to generate software mappings and the chip automatically and rapidly. In this paper, we are trying to solve the first two challenges with our framework. A general approach to hardware-software co-design is to design a unified intermediate representation (IR), and then partition, optimize, and synthesize software and hardware paths based on the IR. However, it is very difficult to design such a unified IR or synthesize arbitrary hardware. We can simplify the IR design by focusing on tensor computations. Since tensor computations can be represented as nested loops, we can build an IR containing the loop and tensor information. In this way, the hardware and software partition is to partition the loops. Then we use spatial accelerators to implement some subloops and the software code to implement the remaining loops. Dedicated hardware usually support one or a set of specific functions. We call these functions as hardware intrinsics. For example, the hardware intrinsics of Google TPU and Tensor Core are matrix multiplications. The hardware intrinsic of MBDLA includes 2D convolution, pooling, activation functions. Tensor computations can only be accelerated by calling these hardware intrinsics. We can abstract many dedicated tensor computation chips as spatial accelerators. A spatial accelerator usually consists of a processing unit array, a scratchpad memory, and a controller. The code on the right is an example of accelerating 2D convolution with the gem intrinsic. The gem intrinsic can only handle matrix multiplications with a fixed size. The fixed size is determined by the PE array. Calling the intrinsic directly from the CPU causes a large number of short data transfer, which is very inefficient. Therefore, we need a hardware-software interface to transfer data in burst mode and call the hardware intrinsic multiple times. We define this hardware-software interface as tensorized. Essentially, the tensorized interface decides how to define and map a tensor computation onto an intrinsic. We have many tensorized choices. Here is an example of accelerating gems with different hardware intrinsics. When the hardware intrinsic is GEMV, we can treat the columns or rows of a matrix N as the vectors in GEMV. However, the output of the second choice is not correct. Therefore, the choice is illegal. When matrix transposition are allowed, we can treat the rows of M as the vectors. When the hardware intrinsic is vector addition AXPY, we can also multiply an element of N with a row of N to match the AXPY pattern. These choices have different impacts on data padding, reuse, and locality. We need to identify and analyze the various tensorized choices. More importantly, hardware and software design spaces are still large even after we've made the tensorized choices. In addition to performance, hardware DLCs involve multiple optimization objects such as power and area. Each point in the hardware design space represents an accelerator instance. Evaluating design points may require prototyping accelerators, which is expensive. On the other hand, software DSE is typically performance-driven, and performance can be evaluated quickly when we fix the hardware architecture. As the hardware DSE and software DSE has different objects and evaluation costs, we need different exploration algorithms. To solve these challenges, we propose Haskell, an Agile code design framework for tensor computation. In the code design process, Haskell first partitions the overall design space into a hardware space and a software space. Then, it explores the design spaces to generate a holistic solution composed of a dedicated accelerator and software programs. Finally, Haskell evaluates the solution. If the solutions cannot meet the user's constraints, Haskell will start a new round of exploration. To perform hardware-software partitioning, we use tensor syntax trees to express different partitioning methods, namely tensorized choices. In the tensor syntax tree, each internal node is an operation, and the children of the nodes are operands of the operator. Each leaf subset of the syntax tree can perform a sub-workload. For instance, we can find 2D conv, gem, dot product, and GEMV sub-workloads in a 2D convolution. Ideally, all these subsets are possible tensorized choices and form the entire partitioning space. However, when the hardware intrinsic is given, only a part of tensorized choices are legal. Hence, we use a two-step matching to examine whether a sub-workload matches the hardware intrinsic. Take matching a 2D convolution and a gem intrinsic as example. We first represent 2D conv into compute tensor syntax tree. Then we perform index matching and structure matching. In the first index matching step, we enumerate the leaf subsets of a compute tree and determine whether a subset can form the hardware intrinsic. For example, the first and the third subset cannot establish a one-to-one mapping to the intrinsic tree, thus cannot be accelerated. In the second structure matching step, we check whether the subtree formed by a subset is isomorphic to the intrinsic tree. Here, the second sub-workload has unmatched internal nodes, thus it is illegal. When a set of these nodes passes the two-step, it represents a legal tensorized choice. By the two-step matching, we can find out all the partitioning methods. Once the hardware and software are partitioned, we start to explore the design space. In Haskell, Hardware and software are optimized jointly. Hardware DSCs use software latency as a metric, while software DSC customize software mappings for hardware architectures. Haskell explores the hardware parameters to optimize performance matrices, as the correlations between the parameters and the matrices are complex. We treat the exploration as a black box optimization. The optimization object is to find the hardware parameters that maximize the performance matrices. As the matrices are multidimensional, there is a parallel set of hardware parameters. We use mobile, multi-object Bayesian optimizations to solve this black box problem. Bayesian optimizations first sample and evaluate design space to build a surrogate model containing prior information. Then it keeps observing new hardware parameters and matrices and updates the surrogate model. In this way, the surrogate model can predict better hardware parameters. Compared to other black box optimization methods, mobile can find good solutions in fewer iterations, which is significant to the costly hardware DSC. We use software primitives to define software design spaces. Software primitives include reorder, split, and fuse. A software optimization is a sequence of software primitives. In the example on the right, the primitive sequence means that we first split the Y, K, and C loops into 6 subloops and interchange all loops in a specific order. Then we fuse the 4 outermost loops into 1 loop and specify the 3 innermost loops as a tensorized sub-workload. We generate software optimizations by reversing the primitive sequence. In the first step, we measure and record the latency of each candidate sequence. Generally, the lower the latency is, the more valuable the sequence is. We select the most valuable sequence for further revisions. Then, when revising a sequence, we also have different revision choices, such as changing the combination of the primitives or change the factors of a primitive. We use Q value in the Q-learning algorithm to evaluate each revision choices. Through iterations of those 2 steps, we can get the final software optimization. Next, I'm going to give an instruction on the installation and usage of Haskell inside of the AHS framework. Running Haskell requires all 4 components in AHS, and it takes about an hour, so please install before the tutorial. You can use a shell script to install everything. We tested these scripts on Ubuntu 20.04 LTS. If you use another OS, or if you use Anaconda or virtual environment for Python, you may need to modify it yourself. For Windows users, it's best to use WSL. Alternatively, you can pull our Docker. We had everything prepared for you. For details, please visit our website. In this tutorial, we provide a Python API as the user interface. First, we need to define some parameters. The D type is the data type. The method is how we estimate hardware performance. There are 3 choices: model, profile, and simulate. In this tutorial, only model is supported. We use Tanit as the model. The constraints define the limit for latency, power, and area. Haskell will find some parallel solutions within the constraints and get the best solution for each one. STTS is the space-time transformation matrices that will be passed to Tanit Tensor. We will talk about it in the next slides. Hardware space define the choices for hardware parameters, which will also be talked about in the next slides. Second, we need to define the hardware intrinsic. We need to define a generator to generate the corresponding hardware. In this tutorial, we support 2 intrinsics, gen and con, due to the reuse restrictions on Tensor. Third, we need to define our benchmark. The benchmark is fetched from the models of Keras. We will test them layer by layer. Eventually, we call the co-design function, put everything we define into it. Then we need to specify how many initialization and iteration trials we needed. The more the The more trials, the better result. Also consumes more time. The hardware space parameter we skipped in the last slide is a dictionary. Each item describes a set of choices for the hardware DSC. X and Y is the width and height of the P array. DMA bus width is the bus width between the scratchpad and the DRAM. Dataflow is the name of the data flows described in the space-time transformation matrices, which you will see later. We need to define a set of space-time transformation matrices manually, each with a name. The names is passed to the hardware design space, so the hardware DSC can find the best one. The STD matrices will be passed to Tanit Tensor, each converted to their input form. In this tutorial, Haskell uses Tanit as the hardware model. The hardware DSC finds a set of hardware parameters. Then it is converted into 3 input files of Tanit. Tanit reads input files and gets some results. We read the feedback and convert the results into latency, throughput, and power, and so on. And those messages will go to the hardware DSC, and they will find better params again. Tanit focuses on data transfer and does not directly produce the messages we need, like throughput and power. So we need a transform formula. The latency is already given by Tanit. You can get the throughput according to the latency. Tanit does not know about the target hardware and thus cannot estimate energy. In AHS, we need 2 factors provided by the user, transfer factor and workload factor. Transfer factor is how much energy is needed to transfer 1 unit of data to the chip, and workload factor is how much energy is needed to do a unit of calculation. Then we can get the power by dividing energy with latency. We also provide a command line interface in this tutorial. We use haskell.py as the command line interface. The command line interface needs an input JSON file, which defines the hardware spaces and space-time transformation matrices. We will talk about it later in the demo section. The output of Haskell lies within the result directory. There are 3 components. A CSV file will provide a summary, which tells the hardware parameters of each Peralta solution. In the software folder, there are some IRs created by Flex Tensor. Each corresponds to a solution in the CSV file. In the hardware folder, there are some configured JSON files for TensorLib and the Verilog generated by it. They also correspond to the solution. Next is the demo section.
Okay.
Hello, everyone.
Sorry. Okay, so I already see some questions, but I will leave the question in the end in the end of the first session. So now we will move to the demo session. Okay, so I will ask Zizhuang to do the demo. Yes.
Li Qiangru from Peking University. It's an honor to be here to share Tanit.
Hello everyone, I'm Zizhuang Luo. In this part, I'm going to give you a step-by-step demo. Here is the directory for this tutorial. You can see that the 4 components of AHS are listed here. Flex Tensor, Haskell, Tanit, and TensorLib. Haskell requires Tanit and TensorLib from the external. So we need to compile Tanit first. Let's cd to Tanit. We assume you already run the init shell script. So all the requirements of Tanit are installed in the external library. all we need to do is make the command line interface for Tanit. Also, we need to make a special version of Tanit for Haskell. This is because Haskell need to call Tanit for many times. So we make a very fast version of Tanit just for Haskell. Now we need to edit the bash.rc file. Here we need to write load library path, and so that we can link the libraries into the executables of Tanit. We also need to modify the TVM home and AX home path of Haskell. Our install script should have done all this for you, but you may need to check it yourself. If you don't use bash, you can edit another RC file of your own. And don't forget to source the RC file. Now let's go to the Haskell directory. Okay, we can see in this directory there are some files. The haskell.py is the command line interface of Haskell, and there are 3 directories here. The source directory is for the source code, the test bench is for the test code, and the result will go to the result directory. Let's see the source directory. The source codes are divided into multiple subdirectories. The most important ones are inside the code design directory. First, we need to modify the config.py. Here are some important paths that we need to modify. First is here, Tanit path. It should link to the interface executable of Tanit. And here is the TensorLib path here. It should link to the path of the home directory that hosts TensorLib. Our install script should be already modified these 2 paths for you, but you can check it yourself. Also, you may want to change the Tanit params here. Here's are the params that to convert the Tanit output into some matrices of Haskell. Now let's see explorer.py. This is the most important file in Haskell. In this file, we define the hardware space and the code design function. Here is the build hardware space function. You can see that we make some parameters for the hardware DLC. You don't need to worry about it, since in this tutorial we have prepared a JSON file to define this hardware space, and we already passed it, so you can just ignore this function. And here is the code design function, which is the most important function in Haskell. It defines the hardware-software code design process. First, Haskell will build a hardware space, and then it will start the mobile-based exploration. First, it runs some initialization trials. Then here, it iteratively update the points. For each iteration, we get some Pareto results and store them. Eventually, we want to print the Pareto results. For each constraint, we will find the best one for it, and we'll call FlexTensor to generate the software for it, and call TensorLib to generate the hardware for it. Now let's see the Python API we just showed in the PPT. In the test bench directory, you can see many predefined scripts for you. Let's see, call mobile net conf. This is the Python API that we have just say in the PPT. First, you need to import everything from Haskell. Then you need to define the parameters here. And then you need to define a conf generator and a mobile net v2 benchmark. Eventually, we put everything into this code design function and you start running. Now let's run this file. Now it is running. We can see that we are running the mobile net v2 Keras model. It has 53 layers, and it took hours to run. So let's stop here and just go to the result. We put the result in the example results directory. You can see there are 3 components here. A CSV file, we can read it. In here, we can see for each constraint, we find a Pareto solution. For example, the first line is the solution that has the least latency. It uses an 8x4 P array, the NVDLA data flow, and a 256 of bus width. And we can see the software folder. The software folders are some IRs produced by Flex Tensor. We name the files according to the parameters. You can see one. We can see this is an IR produced by Flex Tensor. I will not explain here. We will explain it in the Flex Tensor section. And now let's go to the hardware. Let's go to the hardware folder. You can see there are 2 types of file here, JSON file and V file. The JSON file is the input for TensorLib. It describes the parameters we just searched in the DSE. You can see it's a conf benchmark with 8-bit width and some lengths of each loop and the STT matrix. This file goes to TensorLib and it provides a Verilog file. You can see one file. This is the Verilog file provided by TensorLib. We will show how to use it in the TensorLib section. We can also see another script, test bench code exception gem. You can see in this script, we modify the generator as gem. So it provides a gem intrinsic. Also, it goes to the exception benchmark. You can modify it yourself. Like, for example, the constraints, you can modify the constraints into like 200 in latency and 20 in power and so on. And you can also run this file and you will get a similar result just like the last one. And eventually I'll show you the command line interface. Here's the help text. We use -i to specify the intrinsic, -b to specify the benchmark, -f to specify a JSON file. This JSON file describes the things we defined in the Python API. You use -l to specify the limitation on latency, -v for power, -a for area, and double minus init for numbers of initial trials, double minus iter for numbers of iterative trials, double minus d type for data type, and double minus method for the DSE method. We can see one JSON file example. In this JSON file, we define some STTs, just like in the Python API, and some hardware space. It's also the same with the Python API. And let's run this file. Run the command line interface. We can specify the intrinsic of as gem. We can specify the intrinsic as gem, the benchmark as resnet 50, and the input file is the JSON file we just showed, and some limits on latency, some limits on power, and some limits on area. now it is running. And also, it took so many times, so we will stop here. And that's all for the Haskell demo. Now it's for the QA section.
Okay, let me see what question we have. So I will answer starting from the top. So does Haskell support sparse tensor? So far, so the AHS, we have 4 tools, so we don't support the sparse tensor. So we assume the input tensor is dense. But for the sparse, actually, there are multiple ways to solve the problem. If you can change the program to remove this if-else statement and append a multiply in the end, then we will natively support that. But if your sparse computation requires sophisticated if-else statement, currently we don't. Is it possible? The next question is it possible to use hardware cost model other than Tanit? Yes. In fact, actually, we try different approach. One is to use Tanit. We also use. We can also try to use another tool, actually, which is shown last year in micro. It's called Mistral. It's from the Georgia Tech Touchard's group. So we can use other two as well. Okay, so okay, so the next question is, what's the motivation to use Bayesian optimization for hardware design space? And so we use this multi-object Bayesian optimization is because for the hardware, it's very expensive to do the profiling and performance evaluation. And this multi-object Bayesian optimization can reduce the number of trials compared to the other machine learning technique. So that's why we use that. Next is, did you try integrating existing IR, MAR in your hardware software co-design interface? Okay, that's a very good question. Right now we don't we don't support MLR, but that is one of the potential direction for us. Right now, the IR we use actually is the one we propose for the hardware software co-design. It is a tensor syntax tree. So the last 2 question is, does Haskell support tiling? Yes. So in this software optimization, tiling is one of the key optimization log. So the last question is, what's the input format for loops to Haskell? Okay, so for this part, actually, we have a domain-specific language to describe the loops and also the other hardware constraint. So actually, I think that this question is already answered in Zhang's lab demo session. Okay, so I think we have already answered most of the questions. If you still have questions, please leave. We will answer in between. Okay. So now I will move to the next technical talk, and that is the Tanit. So Tanit is one of the tool that will be called by Haskell, used for the data flow modeling.
Tanit tutorial. Tanit is used for modeling tensor data flow based on relation-centric annotation. Tensor application is everywhere in recent AI scenarios. For example, matrix multiplication and convolution are 2 well-known tensor kernels in deep learning algorithms. In the image processing, we often use tensor operators, and the recommendation system usually involves computation with multi-dimensional kernels. Here, I depict some important tensor kernels. The green blocks represent the data dependency between input and output. All these tensor kernels can be written as perfect loops like this. In this slide, instance means the innermost computation. we can find that the computation pattern of these kernels are quite different. For example, they involve various tensor size, and the reduction of partial sums also differs in different kernels. Another important feature of tensor kernels is that they are very regular. Regular means it exhibits high parallelism besides. Hence, operations often show huge amount of computation size. Therefore, various tensor accelerators have been proposed in both academia and industry. Here I present three well-known accelerators. They are Google TPU, Tanit chip, and the Huawei Ascend chip. They all apply spatial architectures, which includes a large P array for parallel computation. The main component of spatial architectures is the hardware data flow that determines how accelerator processes a computation. So what is the tensor computation data flow? Actually, it is an abstraction of the overall computation process, such as how to parallel the computation, how to specify the data movement. Here I picture the computation data flow of three tensor accelerators. The first one is the syntonic data flow of Google TPU. You can see that the data moves between adjacent P's, and on a boundary P will load data from memory. The second one is the multicast data flow. In this data flow, one tensor element is broadcast to multiple P's. The last one is the 3D data flow of Huawei Ascend chip, where data are accessed vertically. Actually, there are various data flow choices when accelerating tensor computation. As said before, we have multicast and the syntonic data flow. Even for the syntonic data flow, we have many variants, like output stationary, input stationary, and there are many other data flows, like row stationary data flows of arrays, a combination of multicast and syntonic data flow, and the reduction tree data flow. The reduction tree data flow means that only top nodes perform multiplications, and the results are gathered by a tree. Facing tremendous data flow choices, it is hard to figure out which one has the lowest latency or which one has the lowest bandwidth requirements. Therefore, we hope to have a framework that can quickly evaluate these data flows to guide the architectural design. To build such framework, we first need a mathematical notation that can formally describe the data flow. That is, the notation should describe where and when a loop instance is executed. After we have a data flow notation, we then need a performance model based on this notation to evaluate some critical performance metrics, such as throughput, data access, bandwidth requirements, and latency. Now let me introduce two existing notations. One is the compute-centric notation. This notation uses some primitives to describe the hardware data flow, such as which loop is paralleled or pipeline. Another notation is data-centric notation. This notation starts from data allocation in time dimension and space dimension. The limitation of these two notations is that they are less expressive, therefore leading to limited data flow design space and less opportunities for optimization. For example, when the time step is a affine transformation of multiple loop dimensions, data access are spooled. Such complex data flow is not involved in the design space of these two notations, while our relation-centric notation is inherently support such complex data flow. Overall, our notation shows a complete design space. For a certain tensor kernel, we have more data flow choices for optimization. Here, the complete means the data flow for perfect loop nest. As for the performance model, previous notations apply a coarse-grained approach. For example, here I read an example of computer-centric notation for matrix multiplication. This notation applies parallel primitive to indicate the computation data flow. When estimating the latency, this notation only uses simple polynomials like dividing iteration numbers by parallel factors. While our approach regards the entire data flow as a relation set, we calculate the latency using integer set operators, which makes our model more precise as we investigate each point in the data flow relation set. Now I will introduce our relation-centric notation in detail. The first question is, what is a relation? Relation actually is the mapping from one thing to another. Our notation features three key relations. They are data flow relation, data assignment relation, and the interconnect relation. As aforementioned, the data flow relation maps the instance in the iteration domain to a specific P and a cycle number. The data assignment relation describes where and when a tensor element is used. This relation helps to analyze data movement and reuse. The last relation is P interconnection. If two P's can share data via a network on chip, we then build a relation between them. By putting these relations together, we can precisely model the tensor data flow on spatial architectures. Here I use matrix multiplication on symbolic array as examples to make a better understanding of data flow relation. In the first example, each output element is kept stationary. Therefore, each instance Sijk is mapped to Pij. While two input tensors are streamed horizontally and vertically, the schooled access resulting in the execution sequence is a linear transformation of 3 dimensions. In the second example, the input matrix is kept stationary in the P. Using relation-centric notation, the data flow is read like this. And we can see that these two notations are very concise, and we only need 2 simple statements to describe the data flow, and it can precisely tell the hardware behavior. This slide shows how to map instances to the P array step by step. The left part is a set of instances. I use output stationary data flow as an example. Here is the data flow relation that tells the PID and the execution cycle. For example, according to the relation, this instance is mapped to the first P with the cycle number 0. Similarly, the first 4 instances are mapped to this P at different cycle number. Here, the data flow relation acts like a bridge that links a set of instances to a set of P's and cycles. The next relation is the data assignment relation. This relation helps to tell a certain type of data is used by which P and at which cycle, or inversely for a certain P at a certain cycle which data is used. First, based on data flow relation, we know the relationship between instance and P's, and the relationship between instance and cycle numbers. Then the tensor kernel tells the relationship between tensor data and the instance. By combining these 2 relations, we know the data assignment relation. After we have data assignment relation, we get the details of the data usage across different P's and cycles, which helps to analyze the data reuse and data movement in our performance model. The last relation is P interconnection. If there is a data path between 2 P's, we will build a relation between them. The systolic relation is formulated like this. We also support some other interconnection topologies. The interconnection relation is used as a constraint when checking data reuse. For example, the data A is used in adjacent P's at different cycles. If there is an interconnection between them, then we can say that this data is reused. If not, we assume this data is read twice from the buffer. Next, I will introduce the methodology of our performance model based on relation-centric notation. First, Each relation is an integer set. All metrics are calculated using set operators. Before we formulate various hardware metrics, we first define three basic volumes. The first volume is a reuse volume. Just as the name says, this volume sums the reused data. For example, the blue plane is tensor domain, and we show the used data across different cycles. Here, each point in the green part is a reuse volume, as it is always reused in the next cycle. And the second one is unique volume, which represents the minimum data size that are required to load from memory. In this figure, the points in the blue part are the unique volume. The last volume is total volume, which is a total number of data that are used. As shown in this figure, reuse volume plus unique volume equals to total volume. Here I show the details of how we calculated the volumes. We use reuse volume as an example. First, we have the data assignment relation set of cycle 2 and cycle 3. Then we use intersection operator to find the reused data. When we find which data are reused, we will check this data is reused in the same PE or can be accessed via interconnection. If so, this data is added to the reuse volume. And the total reuse volume is calculated by summing all intersections between two adjacent cycles. The reuse volume is further divided into spatial reuse and temporal reuse, which describes the reuse occurs in different PEs or in different cycles. To avoid overlap between spatial reuse volume and temporal reuse volume, we restrict the temporal reuse whose data is reused at the same PE. After we have these basic volumes, we can define several hardware metrics. For example, we can estimate the average reuse number of a certain data once it is fetched from the scratch pad. And we can formulate the latency of read, compute, store using unique volume. We can also derive the required bandwidth, including interconnection bandwidth and scratch pad bandwidth. Next, I will show how to use Tanit framework. Tanit supports command line to run the code. We can get the usage of Tanit using help command. To run Tanit, we need three input files. The first file is the PE array file, which describes the PE array size and the PE interconnection. The second file is the state file. This file tells what tensor computation needs to be analyzed. It is written in relation notation. The last file is the data flow file that maps the tensor computation to the PE array. This file has two lines. One is a spacestamp that maps a statement to a specific PE. The other is a timestamp that maps a statement to a specific cycle number. Okay, I will show a step-by-step tutorial of how to use Tanit to model a data flow. We use two-dimensional convolution as an example here, which is stored in the state file. In this file, there are 5 lines. The first line contains 2 numbers. The first one means the number of input tensors, and the second one means the number of output tensors. The second line specifies the loop boundary. S is the instance. The index in S is the loop index. The rest 3 lines are access functions of tensors, which also indicate the date dependency. The access function is written in relation notation that maps the loop index to tensor index. Here we assume that the output is generated by multiply and add operation between input tensors. Then we need to specify the P array size and the P interconnection. In this example, The P array is in a rectangle shape. The interconnection is set to syntonic array, where data can vertically and horizontally traverse between P's. In the third line, there are 4 numbers with different meanings. The first one is L1 size, or scratch pad size. The second one is L2 size, or DRAM size. The third one is the available bandwidth between scratch pad and P array. The last one is average pipeline depth, which is set to half of the P array width. All these descriptions are stored in the P array file. Finally, we need to set the mapping file, which consists of spacestamp and timestamp. We use syntonic array data flow as an example here. The spacestamp is relatively simple, where we map the channel dimensions of the instance to the P array. Since the tensor size is usually larger than the P array size, we use mod operator to split the loop into tiles, which is also called Fossey-affine transformation. Then the timestamp is set to an affine transformation that merges 3 dimensions into a single dimension. Since we tile the loop net, we map the outer loop index to the first 2 dimensions of the timestamp. Finally, the complete data flow is written like this. After we finish in the 3 files, we can run Tanit using this command line. Tanit will print the performance matrix. There are 3 involved tensors: input tensor I, input tensor W, and output tensor O. Metrics of these tensors are listed separately. For example, we have total volume that indicates the number of all required data. And we have unique volume that describes the number of minimum data size. Reuse factor means dividing reuse volume by total volume, which is the average number of reuse times of a single tensor. We can also output this matrix to a CSV file. Okay, let's see some experiment results. It only takes 100 milliseconds to model a data flow on laptops using Tanit. This time mainly depends on the complexity of interconnection topology. For 2D convolution with 6 loops, the time for design space exploration is 40 minutes. The exploration time mainly depends on the number of loops. This figure lists the evaluation results of various hardware metrics. The x-axis means different data flows for 2D convolution tensor operation. For simplicity, we only keep innermost 2 dimensions in the abbreviation of data flow. For example, this data flow is abbreviated as this. We observe that some data flows shows long latency. According to the metrics from Tanit, we find that these poor data flows either have low data reuse or low P utilization. In this table, I list several data flows for different tensor kernels. We can see that our relation-centric notation has a larger design space. For example, we have more data flow choices for matrix multiplication and convolution. Therefore, our notation is more expressive and has more optimization opportunities. Besides, this centric notation only targets on deep neural networks, while our notation is more general that can support many other tensor kernels. Using our performance model, we can also analyze the bandwidth requirement on the different interconnection topology. To do this, we need to change the interconnection relation in the P array file. Our conclusion is that increasing connections does not necessarily reduce scratch pad bandwidth requirement. Interconnection network need to take the data movement patterns into account. Tanit also supports to run a complete neural network. First, we need to specify each layer of the network. Each layer is a config file that consists of data flow file, key array file, and statement file. The statement file is determined by the network parameters, and all layers are stored in the MobileNet directory. Then Tanit can analyze each layer of the network in sequence using this command. If we do not specify to print all results, Tanit will only show some critical metrics, including the load latency, store latency, and compute latency, and also average activated P numbers. Similarly, we can also store this data to a CSV file. Here are some results of the real vector. Tanit can precisely calculate the real vector that affects the latency for data transfer. In this figure, we compare our results with Metro. Tanit is more powerful in 3 aspects. First, Tanit supports output reals analysis. Second, Tanit supports multi-dimensional time steps. Third, Tanit supports quasi-affine transformation. Detailed comparison is discussed in our ASCA paper. In summary, we developed a framework Tanit for modeling tensor computation data flow. First, we propose a relation-centric notation, which is more expressive and leads to a complete design space. Then we build a performance model. Our model can precisely estimate performance metrics based on integer set operators. Finally, Tanit is an open source project. We welcome everyone to use our framework to guide the architecture design. We also hope that users can give us some suggestions to improve Tanit. Okay, that's all. Thank you for listening.
Hello,
Okay.
I'm Xiao Yuepeng from
Okay, so that's the talk of the second tool, this Tanit. So now we move to the demo session of this Tanit, and Li Xiang will show you how to use the tools. Okay, Li Xiang, please. Okay.
Hello, I'm Li Qianglu. Okay, I will show the demo of how to use Tanit we cloned from GitHub. Okay, here is the Tanit directory, and we assume that you have finished the installation of Tanit. The head files are in the include folder, and the corresponding source file are in the source folder. And here is the data flow source file. We can see that our Tanit model is built on integer set library, and each matrix is formulated using integer set operators. Now let's see how to use Tanit. First, I will show how to model a single data flow using Tanit. I have prepared the required files in the data flow example folder. We can see that there are 3 files here. The conf.s is the statement file that describes the target tensor application. This file includes 3 lines, includes the boundary of each loop index and the access function of each tensor. And this is a data flow file that includes the spacestamp and timestamp. It maps each instance to a specific P at a cycle number. In this data flow, we choose a widely used data flow example that maps the channel dimensions to the P array dimensions, because the channel dimension shows less complex data dependency and it is easy to parallel. This is a P array file, and it is a constraint file of the P array. It tells the P array size, interconnection constraint. The numbers below indicate the scratch pad size, DRAM size, bandwidth, and average pipeline depth. By putting these three files together, we can precisely know the hardware behavior. To obtain hardware metrics, we only need to input this command. We use P to indicate the P array file, and S means the statement file, and M means the data flow mapping file. Then we can see the critical metrics. In means the input latency to store or require data. Out means the output latency to store or output. Com means the compute latency. Besides, we can see that all P are utilized and the average utilization is 47 Ps. We can also see other metrics using all command. Using all command, Tanit will output the detailed metrics for each tensor, including different volumes, different type of data reuse. For example, for the output tensor O, the real factor is 9, which is calculated by dividing unique volume into total volume. It means one output element is reused by 9 different instances in this data flow. We can also observe that there is no spatial data reuse. We can see that the final latency of this data flow is bounded by the output latency, because the output image size is large, making parallelization in channel dimension requires to read and store output for multiple times. To reduce output store latency, a possible solution is to maximize output data reuse. So here we can use another data flow called output stationary data flow. In this data flow, we can see that output image is mapped to the P array. Then we can use Tanit to evaluate this data flow. We can see that this data flow dramatically reduces the output store latency and shows the same compute latency. However, we can see that the input latency increased 4 times. In summary, we can use Tanit to explore different data flow choices. The next example is how to model a deep neural network using Tanit. We have prepared the demo code in the network example folder. The mapping files and P array files are independent to the DNN model, therefore it is stored separately. The mapping folder includes different data flow choices. For example, this is the output stationary file. And this is a P array file that includes P constraints. The MobileNet directory consists of a config folder and a statement folder. The statement folder is determined by the network parameters. Here we list 5 layers of MobileNet. Each layer is stored in a statement file that gives the layer parameters. For example, for the first layer, we can see that there are 3 files. The config folder includes the configuration of each layer. It links the statement file of each layer to a specific P array and data flow. Finally, we can use this command to analyze the performance of the MobileNet. Here, E means the directory of the config file. And D means the data file. We can see that Tanit will analyze the data flow of each layer one by one and output the critical metrics. Similarly, we can use all command to see all metrics that for each tensor. Okay, here is the tutorial of Tanit.
Okay, let's see what question we get. Okay, so one question we get is, do we compare the final metric obtained by the relation-centric notation with natural? Yes, we do. In the paper, this paper is published in the ISCA 2021. So we compare with natural extensively. We compare with natural in terms of multiple benchmark and also various performance metric. As Deixiang said, so for this comp and gem, we support more data flow than them because of this relation-centric notation is more expressive. And also, but for the performance metric part, because we use this sophisticated integer set operation to do the performance modeling, which is more accurate than this polynomial-based computations. So the next question is, does Tanit hardware model consider P stores when memory bandwidth is less than required? Yes, we do. So that is in the latency modeling part. Yes, so you can check the details of the paper. Okay, so let me see. So we have other questions. So does the Docker include all these tools? Yes, the Docker include the entire image. So all these Haskell, Tanit, Frac Tensor, and the TensorLib are included in this Docker. Oh, so you have problem running the Docker. So okay, we will check into this. Okay, so that is we have already introduced the first tool. Okay, so now we will have a 10 minutes break. Okay, let's resume after 10 minutes. Okay, let's get started. So now we will move to the second half of the tutorial. So in the second half, we still have two tools to introduce. The first one is a tensor lead.
University. I'm presenting Tensor Lead, a spatial accelerator generation framework for tensor algebra. My advisor is Liang Yun from Peking University. This work is also contributed by Total Laboratory. In our tutorial, we have introduced the Haskell and Tanit. Haskell is a hardware and software co-design framework for tensor computation, and Tanit focuses on the hardware data flow modeling with relation-centric notations. In this talk, I'm going to introduce Tensor Lead. It is a framework for the automatic generation of spatial hardware architectures. This figure shows a typical architectural hierarchy of spatial accelerators. Typical accelerators is composed of PE array, on-chip buffer, and controller. The PE array is formed with an array of homogeneous PEs and connected with regular patterns. This brings large parallelism since different PEs can work concurrently and communicate the data frequently, which meets the requirement of regular tensor operations, such as matrix multiplication. The on-chip buffer is explicitly controlled to enable effective data reuse. We take three famous accelerators as an example: Iris, TPU, and Shidinal. They have many commonalities. First, they have multi-level storage, composed of DRAM and SRAM for data buffering. Second, the on-chip SRAM is partitioned with multiple memory banks. It enables concurrent data load and store with larger bandwidth. Third, they are controlled by a unified controller. There is no complex controller in each PE in order to reduce the architectural complexity of PEs. Finally, all of them have PEs from a 2D array, and all PEs have the same architecture. In 2D PE array, data can communicate in two directions, which enables more complex data reuse opportunities. However, we find that different accelerators use different data flows, which is how data is communicated between PEs. TPU uses weight stationary symbolic array. Iris uses row stationary with diagonal interconnection. Shidinal combines the multicast and symbolic data flow. Maori uses reduction tree data flow. For different data flows, the hardware architectures can vary a lot. We can conclude the similarity and difference of spatial accelerator. Firstly, most accelerators use the three-level hierarchy to enable data locality. The near computation storage has smaller capacity but faster speed. Second, the on-chip buffer is generally divided into banks to enable multiple read and write. Third, PEs from a spatial array. The PEs are connected together in the array so that data can be reused between PEs. Finally, they are usually controlled by a unified controller. However, for different data flows, they also have much difference. First, the PE data flows are different. For symbolic arrays, they are weight stationary, output stationary, and so on. And there are some other data flows, such as row stationary and reduction trees. Next, the accelerators can use different PE size. For example, the first generation of DPU uses a monolithic PE array, and Iris uses multiple smaller PE arrays. The computation kernel can be implemented in different ways. Some use Scala, while some use StreamD. The algorithm can also be different. Finally, the network on-chip structure in accelerators can vary in a significant way. The major part is the connection between PE array and the on-chip shared memory. The conventional development process of spatial accelerator suffers with the trade-off between performance and productivity. Initially, the accelerator is written with manual HDL code, which have good performance but bad productivity. High-level synthesis enables developers to use high-level language to express hardware, but the optimization is difficult, leading to performance loss. Recent works combine domain-specific language framework with high-level synthesis. The DSLs, such as Collide, can make the representation of the algorithm and optimization separate, which promotes the productivity of accelerator development. But the performance becomes worse since the high-level code is automatically generated by domain-specific languages. The scalability is also bad because it only supports limited data flow. Some DSL-based works only support a single symbolic data flow. This motivates our work on TensorLib. Our goal is to create a generation framework with good performance, multiple data flow support, and good productivity. Now, I will give an overview of TensorLib. The input of TensorLib is the computation definition and the data flow definition. The computation definition defines the tensor algebra algorithm, and the data flow is described with space-time transformation, which will be discussed later. We follow the idea of domain-specific language to separate the two definitions. So when the user wants to generate different data flows for the same algorithm, he only needs to change the data flow and keep the computation definition same. TensorLib first perform analysis on the data flow based on space-time transformation to generate the data flow type and data transfer direction of each tensor. Next, it uses predefined hardware templates to generate the hardware architecture in a bottom-up manner. First, it generates the P internal modules to build the P architecture. And next, the P array interconnection and D memory interconnection. Finally, it uses Chisel compiler to generate very long code for FPGA and ASIC synthesis. Compared with previous works, we have 4 major advantages. First, we use simple expression to define hardware data flows. Second, our framework supports various data flows, including stationary, systolic, multicast, unicast, and reduction tree. Third, our framework has good productivity. We use reusable Chisel hardware templates to generate hardware. Different hardware instances can be generated with the same hardware template. Finally, our generator can achieve high performance with Chisel-based code generation, since Chisel code can express RTL level information and it is easier to optimize. Now, I will introduce how does TensorLib analyze tensor data flows. We have discussed the relation-based data flow representation in Tanit. We summarize 3 important relations. Data flow relation between computation instance to hardware P index and cycle index. Next, the instance data relation between computation instance to tensor data index, which is a straightforward relation of tensor data accessing. And finally, the data assignment relation between hardware P and cycle index and tensor data index, which directly corresponds to hardware data flow and computation. These 3 data flows can be derived from each other. When 2 of them are determined, the rest one will be generated. In TensorLib, we use the hardware data relation to express data flows. So how to express the hardware data relation? It cannot be generated directly, but it can be derived with the other 2 relations. We use matrix multiplication as an example. Firstly, given an instance index ijk, we can directly calculate the tensor index accessed in this iteration. In this example, the index is AIK. It can be generated with a tensor access matrix. Secondly, given a computation instance, it can find a unique P index and the P cycle index in the hardware to map the specific instance. After the mapping, we can form the indirect relation between hardware execution and tensor data. In our work, the relation between instance and hardware is represented by the space-time transformation. Space-time transformation transforms a loop index into space-time index, which contains the P index and cycle index. It can be processed with a matrix multiplication. For example, when the loop index is 1, 2, and 2, it multiplies with the matrix STT and generates the space-time vector 1, 2, and 5. This indicates that the computation occurs in PE 1, 2, and cycle 5. The space-time transformation is a one-to-one mapping. Two different loop indexes cannot be mapped to one space-time index because each PE can only perform one computation instance at a certain time. With the space-time transformation, we can easily formulate the hardware-data relation. We want to know all the hardware space and time indexes that reuses the same tensor data element. The first step is the mapping from space-time domain to instance domain using the inverse space-time transformation. The second step is the mapping from instance domain to tensor data index domain with the tensor access matrix. To combine the two steps together, we can build the hardware data relation. The same tensor data is accessed at different hardware P index and cycle indices. For example, the tensor data A01 is used at PE00 cycle 1 and PE10 cycle 2. In this way, we can form the tensor data reuse space. Given a specific tensor data index, we can find all the space-time indices that reuse the same data. It forms the reuse space, a subspace of the space-time domain. The reuse subspace can have different dimension numbers, and it determines the interconnection shape between memories and PEs. Each memory bank can transfer one data element with PE array every cycle. First, if the reuse dimension is 0, each PE directly connects with one memory bank without reuse possibility. Next, if the reuse space dimension is 1, each memory is connected with a row of PEs. There can be multiple possible cases. Here we only show one of them, and details are discussed later. Finally, if the space dimension is 2, there is only one bank and transfers data to all PEs with two-direction data flow. There are also multiple cases, and we only show one of them here. Here we focus on the 1D scenario. When the reuse space is 1D, the reusable instances forms a vector, but the vector can have different space and time directions. There are 3 cases in total. The reuse vector has space part and time part. If the space part is 0, while time part is non-zero, it means that data element is stayed in PE for many cycles. It corresponds to stationary data flow. Next, when both space part and time part is non-zero, data transfer to another PE after delaying with register, which means a solid data flow. Finally, when the space part is non-zero and time part is 0, the same data element appears at different PEs simultaneously, which is multi-faceted data flow. Next, we show our PE and PE array generation process to implement each of these data flows. The first one is systolic data flow. The data delays for T cycles before sending to the next PE with distance P. In the left figure, data is sent to the right PE every 1 cycle. In practice, P is 1 for most systolic arrays. Inside the PE, data from input port is sent to output port and computation cell after delaying with shift registers. The second one is multicast data flow. Data is directly sent to different PEs at the same time. The PE architecture is simple with direct input and output port. However, for output data, different outputs are generated simultaneously, and the result is sent to a reduction tree to generate the final result. The stationary data flow is more complex. Data keeps stationary inside the PE during execution, but it requires systolic data flow to move data between PEs. It is implemented with double buffer in this figure. One register transfers data with the computation cell, while the other register transfers data with other PEs. The two registers communicate periodically to update data. And the architecture for input tensor and output tensor are also different. After introducing the 3 data flows, we discuss how to build the PE architecture. To build the PE architecture, first we create the computation cell and the input-output port for each tensor, which is the PE basic structure. However, we don't know how is the input ports and output ports and the computer cell connected for each tensor. We mark them as a question mark first. We have discussed the 3 different data flows and designed their inner P architecture for both input and output operands. We show it in this table. With space-time transformation, we can discover the data flow type of each tensor and select the correct module accordingly. The module substitutes the question mark module in the basic structure to build the final P architecture. We use 2 systolic array data flow as examples to show the generation process of P architecture. In output stationary, input tensor A and B uses systolic, while output tensor C uses stationary. We substitute each of the question mark module to the prepared systolic and stationary module accordingly to build the P architecture. In with stationary case, input tensor A and output tensor C uses systolic data flow, while input tensor B uses stationary. So we can also substitute the question mark modules with the prepared modules to generate the P architecture. After discussing the generation of P architecture, we built the interconnection pattern between PEs according to the data flow type and the direction of each tensor operand. The PEs can be connected with systolic, multicast, or reduction tree patterns with other PEs and memory module to form the complete P array architecture. In the first example, tensor A and B are both systolic data flow. The direction of tensor A is 0, 1, and it moves from left to right. For tensor B, the direction is 1, 0, so it moves from up to down. When tensor A changes to multicast data flow, the data from memory is sent to each PEs in the same row simultaneously instead of systolic connection, while the data flow of tensor B remains the same. In the last example, tensor A uses vertical multicast data flow, and tensor B uses horizontal multicast. But tensor B is also tensor here, so the PEs are connected using the reduction tree. Finally, we introduce our interpretation of tensor leaf. Our analysis engine generates the PE data flow and P array interconnection patterns. The interconnection contains PE network and PE memory interconnection. Besides, we have predefined the hardware templates of PE internal modules, PE network modules, and memory modules. Our chisel generator engine generates the entire hardware from a bottom-up manner from PE to PE array to the computer accelerator. First, tensor leaf generates the PE architecture using the computational cell and the data flow configurations. Next, the PE network is instantiated and connected with PEs. Finally, it generates the memory modules and connects with the PE network interface to generate the complete architecture. The P array class can be directly compiled to Verilog code using the Cheeto compiler and can be further synthesized with FPGA or ASIC tools. And last, let's show some experiment results. In the first experiment, we evaluated the cycle level performance of different tensor applications and data flows and showed the normalized performance in the chart. We evaluated 6 tensor applications: GMM, GMV, COM2D, depth-wise COM2D, MTTKRP, and DMC. The data flows include systolic, multicast, stationary, unicast, and broadcast data flows. We find that tensor leaf is able to generate different spatial architectures for different algorithms and data flows, but the performance of different data flows can vary a lot. For example, the performance of GMV is worse than GMM, since the parallelism of GMV is only 1 dimension. For convolution, different data flows also show significant performance variance. We also synthesized our generated code on FPGA with Tanit tools and compared with previous works. Our proposed accelerator achieves 21% frequency and 15% throughput improvement. The Cheeto generated code can be more efficient than high-level synthesis-based works since it directly expresses RTL level information. So register level optimization becomes easier. Finally, let's summarize the talk. We propose TensorLib, a spatial accelerator generation framework for tensor algebra. For data flow representation, we use space-time transformation matrix to represent data flow, and we support various types of data flows. We define hardware code templates and generate the hardware accelerator with bottom-up manner from PE to PE array and its connection. Our code is open source in GitHub. Now, I will introduce how to use the TensorLib tool. TensorLib requires the user input of tensor computation and data flow. It uses Scala API to define computation. We define 7 APIs in TensorLib to represent tensor computation. First, we use gen tensors and gen iterators to define tensor and iterator variables, and use setExpr to define the computation statements. Iterator range and tensor bit width can also be defined. Set latency defines the latency of a computation pipeline, and it also enables users to customize computation kernels with the use custom kernel API. We use matrix multiplication as an example to generate an output stationary symbolic array. The right image shows the data flow of each tensor. Two input tensor flows in a symbolic way, and the output tensor keeps stationary. We follow 3 steps to generate the hardware. The first step is workload definition. The second step is space-time matrix definition. And finally, we call the Chisel compiler to generate the Verilog code. For the workload definition, first, we define 3 iterators, IJK, and 3 tensors, ABC. Next, we set the expression Cij as to the multiplication of AIK times BKG. Next, we define the range of IJK's loops respectively, and set the latency to 1. Suppose all of the bit width is 16. Next, we define the space-time transformation matrix here. It refers to the output stationary symbolic array in this case. Finally, we generate data flow with the gen data flow API, and we call Chisel driver to generate the Verilog code. Instead of running TensorLib with DSL programming, we also provide another way with predefined data flow. The configuration JSON file contains benchmark name, data bit width, length, and space-time transformation matrix. The configuration file can be generated by Haskell, so users can automatically generate hardware without Scala programming. Currently, the configuration file only supports GMM and the convolution benchmark. Finally, we built a tester program based on Chisel to simulate and verify the result of our generated architecture. To run the program, simply type spt run main TensorLib.test underlying GMM in the command line. It creates 4x4 PE array for matrix multiplication and simulates with randomly generated matrices. We can see that the result matches the reference data. While TensorLib doesn't include competition IP generator, it enables users to use the default integer multiply and add IP or create customized IPs. The customized IPs can be wrapped with a Verilog wrapper to be integrated with TensorLib. To use customized IPs, users should define use customized kernel as true and provide Verilog implementation for both computation cell and reduction cell. The Verilog code can be further called user-provided or vendor-provided IPs to implement the customized operations. With the customized kernel, TensorLib can integrate other IPs. For example, TensorLib can integrate the Vivado IP for NVGA interface. First, we define a black box module in Chisel called the Vivado Max, and we use Vivado to generate the IP with the same name to implement the functionality. Afterwards, the project can be synthesized and implemented. We'll show the result in the right figure. We also provide a demonstration on real FPGA to verify its functionality in hardware. We use Xilinx VCU 118 board with VU9P FPGA. We synthesize a 4x4 PE array with Vivado and add some interface modules to communicate data with FPGA memory. We also program FPGA buttons to provide control signals for P array. In our demonstration, the host computer generates random matrices and writes to FPGA memory. The P array reads data from memory and is controlled by the FPGA buttons. It generates output data and writes back to FPGA memory, which can be verified by host computer.
Okay, next I will ask Liancheng to give a demo of TensorLib.
Now let's demonstrate TensorLib in the command line. Here we enter the Docker directory. Here shows the TensorLib folder. The SRC directory contains the source code, and the example directory contains the predefined JSON files generated from Haskell. First, we show how to generate accelerator with the TensorLib API. The code is defined in the SRC main Scala TensorLib and the example underlying gmm.scala. In this code, it is similar as the presentation. We define a operator with an operator spec class. It contains all the informations in the operator we have introduced in the presentation. Next, we define the space-time matrix. Note that the matrix cannot be randomly generated. It must be a full-ranked matrix. So that the generated hardware can be legal. Next, we call the gen data flow function to generate the data flow and call the chisel driver to generate the Verilog code. Now we show how to run the code to generate Verilog file. It generates an 8 times 8 P array, and the memory size is also given. Here we can see the output Verilog file here at parray.v. The Verilog file is very long since it contains memory modules, PE modules, and controller modules. For each data flow modules, such as stationary output, systolic input, they are also included in the generated Verilog files. We can also generate the example for convolution 2D. The code is at the convolution example conv2d.scala. We don't show the code here, and we can run the script now. It generates a different data flow. The input is stationary, while the output is systolic data flow. Next, we also provide an example for example to if the user don't want to write Scala code with TensorLib API, we also provide JSON scripts to invoke TensorLib generator. The JSON scripts can be generated with Haskell, and it contains the similar information with TensorLib API. The JSON file is located at examples folder. To run TensorLib with JSON file, we have to define the JSON path and output path. Here, the JSON file is defined in the example folder. It contains the benchmark name, tensor bit width, tensor iterator length, and space-time matrix. We call the parse.json class to run the I'm sorry. Oh, I'm in the wrong directory. Oh, here it runs successfully. The output will be located in the output directory. We can see the output.v. Next, we show how to test the correctness of TensorLib test code with chisel tester. We run run main TensorLib.test GMM. It generates two random matrices and simulates the PE array architecture to calculate the result. Here we show the two random matrices, and the reference result is the golden value computed by the Scala, and hardware output is the result simulated by with the chisel simulator. We can see the two result matches. Finally, we also demonstrate how to run TensorLib generated code on the real FPGA. Here shows our FPGA. It's the V09P FPGA. We switch to another workspace here. First, it contains some TCL scripts to program FPGA and to read and write data from the FPGA memory. And we first call the generator genbytes.py to generate some random matrices. It generates two matrices and also calculate the reference result. Next, we program the FPGA with the program FPGA.tcl. It writes the FPGA with the synthesized bit stream. The bit stream is synthesized with our generated code with Vivado and added some other modules for data communication interface and programmed FPGA buttons for control signals. Yes, now it's programmed successfully. Next, we call the write data.tcl to write data into FPGA memory. It runs successfully now. If we read the result from FPGA now without pushing the button, we can see the result is not correct. Now we read the data without calling the FPGA, and we can see that the result isn't written into the FPGA memory now. Now we push the FPGA buttons. and read the data from FPGA now. Now we can see the FPGA result and reference result matches, so that we can prove that TensorLib works correctly in FPGA. That's all of my demonstration.
Okay, so I see there are some questions, and Liancheng and I will answer those questions. So the first question is, do you compare the performance of TensorLib with AutoSA, and what makes TensorLib better than PolySA and SUSY? TensorLib actually is submitted. TensorLib will appear in this year deck, and we submitted in last year November. So at that time, AutoSA is not published, so we didn't compare with TensorLib with AutoSA. But in our paper, what we compare with PolySA and SUSY. So the reason we are better than them is because the low-level implementation. So we generate the chisel code, and also we in our template we modify the way we generate the code, and that's why we are better than PolySA and the SUSY. So the next question is, how does TensorLib models task level parallelism? For example, does it require user to give hints such as Vivado high-level synthesis, where it requires data flow directives? No, right now the TensorLib doesn't model this task level parallelism. So this is for a single layer. So if we every time the demo Liancheng just gave actually is for a single gem or single tensor computation. So we don't support multiple tensor computation right now. If we support the way we support this multiple tensor computation is we do a layer by layer computation. So it's not a data flow among these multiple tensors, but we are working on to support the entire data flow, the entire network with this data flow. So the next computation is, it looks like TensorLib has higher resource usage than the SUSY or PolySA. Could you please elaborate on that? Higher resource usage. Actually, I didn't notice that. Do you know why?
The resource usage is due. The resource usage is due to how much DSP we have used to show the frequency. If we use more DSPs use a resource, the frequency can be slowed down since the routing construction. So we can use about 75% DSP resources without degrading the frequency. If we use too much DSP resources, the frequency will also slow down.
Okay, I guess the resource is mainly because we use a different generation techniques. So, but actually we didn't look into the details of the generation of PolySA. But we can check that and answer and answer you offline. Okay, so let me see. There is another 2 questions in here. Okay. Oh, I think that the question is the same in the Q&A box. So actually we already answered that. Okay, so now we finish the talk for TensorLib, and we will move to the next one, that is Flex Tensor. Oh, no.
Hello.
So how to open? Oh, okay. Okay.
Hello, everyone.
Oh,
This
sorry,
is
sorry.
Lisa.
Hello, everyone. I'm Zheng from Peking University. My advisor is Professor Liang. I'm here to share our work Flex Tensor with you, which is a framework for automatic schedule exploration and optimization of tensor computation. We used to say, computing is everywhere. Computing happens when the camera recognizes who you are, when you are searching news from internet, and when you are sitting in the car with autopilot. We also say that we are in the golden area of artificial intelligence. The time witnesses the birth of numerous deep learning networks, including AlexNet, YOLO, and BERT. All these applications are mainly composed of tensor computations. A tensor is a multidimensional array, and the tensor computation is an operation among tensors, such as jam, convolution, and so on. On the other hand, post-model array brings us heterogeneous system. A heterogeneous system is a system with different computing devices, including CPU, GPU, and FPGA. Different hardware varies in architecture, programming model, and optimization. Deploying applications on heterogeneous system presents huge challenges to programmers, which requires expertise in different hardware. It's hard for just one programmer to handle all the devices by himself. As a result, only by teamwork can they achieve the final task, which should take a long time and huge efforts. To fill the gap between hardware and application, many vendors provide highly optimized libraries. Typical libraries are CUDN from NVIDIA, MQ and MKLDN from Intel. These libraries provide high-performance implementations of tensor computations and support the ecosystem of the famous deep learning frameworks such as TensorFlow and PyTorch. But the problem is that these libraries are all hand-optimized, which means they need a long time to come into being, and they require lots of human efforts. As a result, they will fall far behind the rapid evolution of application and algorithms. In recent years, there has been a growing interest in leveraging high-level abstraction to describe tensor algorithms and employing tensor compilers to generate low-level implementations automatically. The compute description is a high-level description about algorithm, which is actually a mathematical expression. The scheduling is about how to optimize a program. It is written in primitives with parameters. On the right of the slide are some primitives. They have different semantics and different parameter settings. For example, the split primitive is used for loop partition, and it requires split factors as parameters. The reorder primitive is used for loop reordering, and it requires a new order as parameter. Here is an example that illustrates the idea of compute and schedule. From the compute description, we can get naive source code which is only a single for loop. And we can use scheduling to optimize the computation by adding some primitives. In this example, we use split for loop partition and unroll for loop unrolling. This is a resulting code, which is potentially more efficient than the naive one. With the compute and schedule, we can generate source code from high-level algorithm and optimization descriptions, which can largely relieve the problems of hand-optimized libraries. In fact, the workflow of hand-optimized libraries is from algorithm to optimization and to source code. All these stages require manual modification and test, which may repeat hundreds of times. What's more, the stages are dependent on each other. Once one stage changes, the other stages have to change correspondingly. This requires the developers to have expertise in both algorithm and hardware. As a result, the whole development process may involve hundreds to thousands of engineers and take a very long time. The results are hardware specific, not portable. By separating compute and scheduling, what we really do is to bring automation to source code generation. As shown in this figure, the last stage is handled by machine. This is a great improvement, but developers still have to handle algorithm and optimization. That is, writing compute and schedule. In this work, we point out that separating compute and scheduling is not enough because finding a good optimization choice can be full of challenge, which requires expertise in optimization, and the result is still hardware specific. Here, we list the limitations of writing schedules. There are many different schedule primitives for different hardware. They can be combined in many different ways in different parameters. It's hard to tell which combination of primitives and the parameter citing is a best for one tensor computation on certain hardware. The developer have to search a huge dense space manually, and the results are not possible. We did some experiments to show the difficulty in writing schedules. In the first figure, C2, C8, and C13 are 2D convolutions of different input scales. Schedule A, B, C differ in primitive combinations. This shows that different primitive combinations and even different input scales can result different performance. The second figure shows the impact of schedule parameters. We use 2D convolution with the same primitive combination but different parameters on different hardware. We can see that the performance varies differently. From these examples, it's clear that writing an optimized schedule on heterogeneous systems presents huge challenges for programmers. So we want a framework of more automation, which requires no manual optimization, less development time cost, and is more portable to new hardware. We want the programmers not to care about low-level programming and use a short time to complete tasks. Here, we introduce FlexTensor, a fully automatic schedule exploration and optimization framework for heterogeneous systems. As the figure shows, FlexTensor brings automation to optimization level. Developers no longer need to write schedules manually. Hardware details are hidden from programmers, so good portability can be achieved. With all concentrations focused on only algorithms. The key idea of FlexTensor is to leverage schedule space exploration to generate a schedule rather than writing a schedule by hand. We show that FlexTensor achieves all what we want. It uses automatic schedule exploration for optimization. It supports CPU, GPU, and FPGA with high performance. It only needs compute description in Python. The development time is about from 10 minutes to 1 hour. FlexTensor is based on previous work of Highlight and TVM. It leverages the idea of compute and schedule from Highlight and the code generation support from TVM. The workflow of FlexTensor is composed of 5 components. The first, static analysis, takes the compute description as input and extracts statistical information and structural information from the description. The statistical and structural information is used by the second part to generate schedule space. Then the third part explores the schedule space and evaluates different schedule configurations. The final results of searching is a highly optimized schedule configuration, which is used to generate final schedules. And the last part generates source code according to the final schedule. In my presentation, I will focus on 3 components: the schedule space generation, the exploration, and the schedule generation. The key challenges of FlexTensor are how to provide schedule for compute and how to guarantee high performance. We propose 2 solutions. The first is to enumerate possible schedule primitive combinations and parameter sightings for given compute description. The second is to use effective exploration with heuristic and machine learning. For schedule space generation, we first use static analysis to get the statistical information as well as structural information. Statistical information includes loop tree counts, number of loops, loop order, and so on. Structural information includes computation graph structure, producer-consumer relationship, and so on. The information is used to enumerate possible primitive combinations and parameter sightings. Different primitives such as speed, welder, and fields are combined to produce possible schedule configurations, but this space is very large. We know that many points in the space are inferior, so we can print them out. So we apply 3 principles during enumeration in order to print the space. The principles are limit the depth of a primitives combination, print parameter space, and predetermine certain decisions for different hardware. After printing, we apply another technique called rearrangement to the space. The purpose is to make the space more easy to explore. The original space generated by the enumeration process is actually a linear list, as is shown in this figure. Such linear list is disorganized and provides little information for exploration. We don't know the relationship of neighboring points, so searching is hard to carry out. We notice that, in fact, many points have similar configurations with each other. We call such similarity structural similarity. If we can gather points with structural similarity together, we can potentially perform a more effective exploration. See this figure? We use similar color to represent similar configurations. If the linear list, we need 8 steps to reach the optimal point. We can possibly make it 2 steps after rearrangement of the space. This is because by gathering similar points together, we construct a higher dimensional space, which shortens the path from the starting point to the optimal point. Now we get the scheduled space. How should we explore it? We want to know the correct starting point, which is near to the optimal point, and we want to know how to move from one point to another through the shortest path to optimal point. These questions are hard to answer by deterministic method, so we turn to random algorithms. We use heuristic method for choosing starting point and the machine learning method to tell us how to find the shortest path. Our algorithm needs evaluations of the point in the scheduled space, that is the execution time of certain schedule configuration. Our methodology is to directly run the schedule on target device and obtain the time cost for CPU, GPU. And we use a cost model for FPGA because the long synthesis time of FPGA prevents us from profiling by running. In the following, I will explain our searching method in details. Our heuristic method is based on simulated annealing. During exploration, we record all the evaluated points, and our starting points are chosen from the evaluated point. One may choose the optimal point known as the starting point. This is the way start. But the risk is you may be trapped into local minimums. So we assign possibility to each point using such formula. The formula says the better a point is, the more possible it will be chosen as a starting point. But there is a chance that an inferior point is chosen. This gives the chances to escape from the local minimums and try new possibilities. We can also choose multiple starting points that is controlled by the user. On the other hand, we use machine learning method to find good directions to search along. First, we discard points that has already been explored. In this example, Q4 is discarded because point 2 has already been evaluated. Then, we use detuning algorithm to predict the Q value for each possible direction. The Q value represents the quality of each direction. The larger Q value is, the better the direction is. So we choose a direction with the biggest Q value to search along. One may ask, how could the detuning algorithm knows the quality of different directions? This is the magic of machine learning. Detuning algorithm uses a simple network to do the prediction. In our experiments, it's just a 4-layer fully connected network. The output of the network is a Q value of each direction. Note that our schedule is of fixed dimensions, so the number of outputs is also fixed, but we may only use part of them. In this example, Q4 is not used because Q4 leads to a point that has already been evaluated. This network requires to be trained. We train the network during exploration process and use the Q values of evaluated points at training site. Our exploration process finally outputs an optimized schedule configuration. We need to generate real schedule according to such configuration. The schedule generation is customized for different hardware. For CPU, register blocking and vectorization are of critical importance. Register blocking are enabled through multi-level tiling. We use split and reorder primitives to do this. Vectorization is also applied to the innermost loop. The trip counts of the innermost loop are determined by split factors and tuned in the exploration phase. For GPU, block thread decomposition and the configuration of shared memory are important. Block and thread decomposition is reflected in split factors and implemented by multi-level tiling. For shared memory configuration, each block always loads data to shared memory before computation. The size of the shared memory used in each block is determined by the trip counts of inner loops, which are also tuned in during exploration. For FPG, we leverage a widely used three-stage coarse-grained pipeline architecture to build tensor computation accelerators. The three stages are data read, compute, and write. The DDR bandwidth, the on-chip memory buffer size, and the total size of transfer data determine the read-write schedules. And the schedule for compute stages is determined by the DSP and DRAM resources. In our experiments, we use 12 different benchmarks. Most of them are variants of convolution, including group convolution, depth-wise convolution, and the transposed convolution. They bear different computing and memory features. From each benchmark, we test several different input scales, and the final result is shown in the form of geometric mean performance speedup and absolute performance. Our baselines are MKLDN, QDN, and hand-optimized kernels. On GPU, we evaluated all the benchmarks. The baseline is PyTorch and QDN. We test the flex tensor on these three GPUs, NVIDIA V100, P100, and Titan N. In most cases, flex tensor achieves the best performance, and we can observe good speedup over QDN on all the three GPUs. Flex tensor achieves good speedup thanks to the exploration of huge schedule space for choosing proper schedule primitives and the parameters. We also use 2D convolution as a case study to show the performance of flex tensor on heterogeneous system. For GPU, we achieve average 1.5 times speedup over QDN. Flex tensor can dynamically adapt to different input shapes and search for proper schedules. The average absolute performance of flex tensor is more than 3.80 blocks. For CPU, the speedup is 1.72 times over MKLDN. 2K optimizations of flex tensor uses are multiprocessing and vectorization. Besides, flex tensor uses NCHWC layout in experiments for high performance. For FPG, the baseline is hand-optimized OpenCL codes from expert. The speedup is 1.5 times over baseline. The important factor to high performance is to solve the optimization problem under hardware constraints by exploring schedule space with guidance of cost model. We also compare to the state of the art. We use AutoTVM as baseline, which requires user to write high-quality schedule templates and perform parameter tuning to find the final schedule. It is semi-automatic in that and relies on XGBoost to learn a cost model. We compare to AutoTVM on several benchmarks. The overall speedup is 2.21 times over AutoTVM. What's more, we also compare the exploration time cost. Here we show the exploration time of three methods. The red one is our method with Q-learning, which is called Q method. The blue one is our method without Q-learning for contrast. It is called P method. And the green one is AutoTVM, which is our baseline. We can see AutoTVM is faster than P method, and Q method is faster than both P method and AutoTVM. Actually, in our experiments, Q method requires less than 30% of the time AutoTVM to achieve similar performance. In conclusion, we design and implement a fully automatic optimization framework for scheduling exploration on heterogeneous systems. We use heuristic and Q-learning to perform efficient exploration. We achieve high performance on CPU, GPU, and FPG. Our work is available on GitHub. That's all. Thank you.
Okay, I will show you how to use flat tensor to optimize DN workloads for different hardware platforms. To use flat tensor, there are two ways. The first way is to download the source code and install all the dependencies. I have prepared a special version of flat tensor on GitHub, and you can download it. It depends on a special version of TVM. And to set up the environment, please refer to our README. The second way to use flat tensor is to use a Docker image, and please refer to our website to get the Docker image. If you have installed flat tensor and correctly set up the environment, now you can run flat tensor. To help you write your own optimization tasks, we have provided some scripts for you, and they are under the optimized directory. And then in this tutorial, I will run 3 of them. The code structure of Flat Tensor is very simple because it's just a pure Python project. And under the Flat Tensor directory, there are main scheduler, the schedule task, and the implementation for search space. And in the baseline directory, there are scripts to measure the performance of PyTorch and AutoTVM. And in the configs directory, I have prepared some input shapes for different workloads. And in the NN directory, you can find the descriptions of different operators. The first platform I'm going to use is the CPU, and I choose to optimize convolution as it is a critical computation workload in CNN. Please open the optimization file just under the tutorial, com2d LLVM, and optimize com2d.py. And you can find there are many command line arguments for this file, and I will explain some important options for you. To get all the options, you can just type Python optimize com2d.py ---- help. And the first option I will explain is the shapes. It specifies which networks you want to optimize. I have prepared some networks for you, including YOLO, GoogleNet, and ResNet. The second parameter you should specify is a target. And in this example, we use LLVM because we will generate LLVM IR. And you can see the CPU I'm using is a Xeon Gold CPU. I choose this CPU because it supports a special VNI instruction, and we will use a VNI instruction in this tutorial. And the log option specifies where to store your schedule configurations. And the parallel option specifies how many processes you want to use in the tuning procedure. It usually takes Flat Tensor more than half an hour to optimize one workload. And in this tutorial, we can't wait Flat Tensor to get all the results. So I have prepared some pre-tuned configurations for you, and you can run the configurations to get the performance numbers. To do this, you should just type Python optimize com2d.py ---- and the name of the log file. You can also get a figure to show the performance of Flat Tensor and the baseline. And in this example, we use AutoTVM as a baseline. And to do this, you just type Python plot.py. You can find the related files in the tutorial directory. The second platform I'm going to use is a GPU. The command line arguments are similar to those of CPU, except for the target, because we are going to generate CUDA code this time. Similarly, I have prepared some pre-tuned configurations for GPU. And one interesting thing is that the configurations are obtained from another GPU, that's a Titan X GPU. But I will run this tutorial on a new GPU that's V100 GPU. But we can see the performance of Flat Tensor is still much higher than PyTorch. You can also add your own tuning tasks to Flat Tensor. And this is an important feature because you may want to optimize some new operators. And all you need to do is to modify the task.py. There are 2 steps required. The first step is to describe a new compute. And I show the example of a special gem where the innermost dimensions are packed together to form a small gem. And this small gem is going to be replaced by a special instruction, that's the VNI instruction, and we will introduce the instruction later. And the second step you should do is to register the optimization task. And you should specify the name, the compute function, the input shape and data type, and the target platform. If you are using flat tensor on CPU and GPU, there's no need to modify the scheduler flat tensor. But if you are targeting a new platform, such as generating a new instruction in this tutorial, then you have to modify the scheduler. And to design a new scheduler, you should use a configure variable to get the parameters of the different schedule primitives, and use a variable to determine how to combine different primitives. I have done this for you for the VNI instruction, and you can check the new scheduler of flat tensor in the source code. Let's talk about the intrinsic generation. We call special instructions intrinsic, and flat tensor supports new intrinsic generation. You can register your new intrinsic in intrinsic.py, and remember to register how to get the third space for flat tensor in the space.py. To register a new intrinsic, you should write two things. The first is the compute of the intrinsic. Yes, the intrinsic has its own compute, because the compute tells what computation does a special instruction do. And the second part is how to generate the IR for this intrinsic. It's a bit complex, and I have done this for you. You can try VNI instruction in flat tensor now. After registering the intrinsic, the remaining question is how flat tensor knows where to apply the special intrinsic in the given operator. The solution is AST matching. That's to find a subtree in the AST of the compute operator that is isomorphic to the AST of intrinsic. And by doing so, flat tensor knows which loops match with the loops of the intrinsic, and these loops will be tensorized and replaced by the intrinsic. For example, in the convolution, we can find a gem, and in this tensor-tensor multiplication, we can find a GMB, and these matched loops will be replaced by special intrinsic by flat tensor. Okay, now we are ready to use flat tensor to generate VNI instruction for different operators. And in this step, we show how to optimize a gem with VNI instruction. All the configurations are similar to the previously introduced ones for CPU and GPU, except for that we should specify Cascade Lake as our target platform this time. Because the CPU we are using, the Xeon Gold CPU, is the Cascade Lake CPU. And remember to specify the data type as integer precision, because the VNI instruction is designed for integer computation. And similarly, you can run the pre-tuned configurations for this example, and you can run the plot.py to get the performance figure, and you can see the speed up of flat tensor to NumPy is impressive. This is because as far as I know, the NumPy doesn't use VNI instruction, and it can't get the acceleration from hardware. If you want to see the generated IR of flat tensor, just pass a dump IR option to the script, and it will print the intermediate representation of the operator. And you can see in this example, we can find the LVM intrin, and the ID of the intrinsic identifies as a VNI instruction. Okay, at last, if you want to learn more about flat tensor, please visit our group website and read the publications. Thank you.
Okay, so now I will ask Sida to do the demo.
Okay, I will run the code for you. And first, I have opened my VS Code and connect to a remote server because I'm going to use some different CPU and GPUs. Okay, as you can see, we are in the root directory of FlatTensor. And the first thing I'm going to do is to open a new terminal and set up the environment. Then let's move to the root directory of FlatTensor. And you can see we have the baseline directory, the configs directory, the example directory, and so on. And in this tutorial, we are going to use the files in tutorial directory. And you can see there are 3 folders in tutorial directory, and 1 for GPU, 1 for CPU, and 1 for the special VNI instruction. Let's start from the CPU platform. You can see I have prepared some files for you, and the main file is optimize count2d.py. Open this file, you can find there are many command line options, and I will explain the options for you. The shapes as specify the networks you want to optimize, and the trails specifies how many trials you want FlatTensor to try to optimize the workload. And to run the FlatTensor from scratch, you can use a command in cmd.md, this file. And we will run the first one. Okay. And you can see we are optimizing ResNet and targeting the CPU platform. And we use 8 processes. FlatTensor is running, and it tells you some useful information. It says that you are optimizing a convolution layer, and this is an input shape. And the total optimization space size is very large. But for the graph space is small because we are just optimizing 1 layer, but the operation space is very large. FlatTensor is warming up by randomly searching some configurations, and these numbers are the performance of these configurations. It takes a long time to optimize a workload, so I will just stop here. And you can see I have prepared some configurations for you. The configuration for totally 20 layers of convolution. And we can run the configurations and to get the performance. So we are going to run the second command. I will just type. So FlatTensor is running, and this is a case number, and this is a execution time for the case. There are totally 20 cases, and we have to wait several seconds. FlatTensor will run each case hundreds of times and report the average execution time. Okay, it's done. And I will explain the baseline file. This file is used to measure the performance of our baseline, for example, AutoTVM and PyTorch. And the plot file is used to run FlatTensor first and run the baseline secondly, and at last print a figure to show the performance comparison. You can see this is a result figure. Then let's go to the GPU platform. And you can see I have prepared similar files for you. And you can get the usage of these files by typing optimize count2d ---- help.
The options are actually the same as the CPU, but the only difference is remember to specify target is CUDA this time. So for the GPU example, we can directly run the plot.py to get a new figure, a new result figure. This is an old one I have run before, and we will get a new one. We have to wait several seconds because Flat Tensor have to compile the code and run each case hundreds of times. During this time, we can check that what baseline we are using. We see the plot file, and we are using PyTorch. And we will check if PyTorch is using CUDA. And you can see here, we enable CUDA backend, and PyTorch will be faster when it uses CUDA. Okay, you can see it's done, and we get a new figure here. And you can check the performance of Flat Tensor. It's a red bars. If you want to inspect the generated code, and in this example, it's a CUDA code, you can add a new option. That's optimize com2d.py, test the ResNet optimize log, and the dump code option. We will dump the code to a temp file so we can check the code easily. The file is generated. You can see the generated CUDA code is very long, and the code is specially optimized for the convolution workload. So you can check the code yourself, and I will stop here. Okay, let's run the final example, and we will use a VNI instruction. Let's move to the gem VNI, and this time we are going to optimize a gem workload. You can see here is also an optimized file. It's called optimize gem, and you can get the usage of this file. It's similar to the convolution optimization file. And you can see the relevant commands here. To run Flat Tensor from scratch, you can specify the target. I will copy the. Okay, remember to specify the data type. And remember, we are using Cascade Lake this time. You can see Flat Tensor is running, and the optimization space is smaller than convolution because gem is simpler than convolution. And to get the generated IR, I will use pre-tuned configurations that's in the gem optimized log. Here are configurations for 37 gem input shapes. And you can get the IR by typing optimize gem and test the gem optimize log. And remember to add the dump IR. Also, we will dump the results to a temp file. And you can see the generated IR. It's very long. And you can see the LLVM entry here. Okay, that's all my tutorial, and thank you for listening.
Okay, let's see what question we have. Okay, so I think we don't have any new questions. So let me do the conclusion. So we have developed this AHS framework. It's an agile framework for hardware software co-design. In particular, we introduced 4 tools. They are Haskell for hardware software co-design, Tanit for data flow modeling, and the Tensor for the data flow hardware generation, and Tensor for the software optimizations. So together they can be used to do the hardware software partitioning and the design space exploration of the hardware and software. Okay, so if you have any further question, then you are welcome to reach us. So you can find our contact email at the AHS website. So that's all of today, and thank you for attending.